Hello everyone. Today we will present our project, myself and my colleague Muhammad Ali, our project for design of renewable DC system for a house in Canada. In the past 50 years, many renewable projects have been established worldwide using various energy sources such as solar, wind, and other renewable energy sources. Wind and solar energy continue to play an essential role in this field as they are the most widespread renewable energy source worldwide. The overall efficiency of the most of the means of electricity production using renewable energy is much lower compared to non-renewable energy sources. In this project, we will focus on solar power as a source of energy to generate electricity in the form of DC voltage to partially feed a house in Canada. The conversion of solar energy into various forms, such as electrical and thermal energy, is known as solar energy. Solar energy is widely recognized as the most environmentally friendly source of energy. The optimal design of a grid-connected rooftop solar system for a university campus in Orgla, Algeria, has been explored by Mukhtar. During the research, they used many programs that help in renewable energy design, such as Ecotech, ARC, GIS, and Homer Optimizer, in the project to reduce the cost of energy and at the same time increase the power received from the sun. Many studies examined the feasibility of installing solar energy system on the roof of building. Asif and Ghalib explored the technical feasibility and used different surfaces for installing PV systems. Solar tracking systems have different methods of classification. They can be classified based on the various forms of control, the extent of freedom of movement, and the type of driver used. The solar tracking systems may be very useful in energy generation. Trackers are often used in fixed structure PV panels system to lower the angle of incidence between sunlight and the PV panel. With this groundbreaking technology, the solar energy industry is gradually developing as the most cost-effective renewable energy choice accessible today. For the solar tracking control system, there is two types of systems for control. First one is open loop tracking system, secondary closed loop tracking system. For the open loop system, the system employs an operation algorithm and only the most current data input to give a controlling signal to the motor through a control unit. It lacks the benefits of tracking and analyzing output data about the expected output, although the implementation is less expensive and easier to use than a closed-loop monitoring system. There is no debugging process, therefore it's up to the algorithm to verify that the intended result is reached. This open-loop method was compared with standard and straightforward tracking algorithm, which rotates the panel at predetermined interval from sunrise to sunset, which is the same number of daily reorientations, to assess its effectiveness for the orientation of the solar PV system. Solar tracking closed-loop system. A system of closed-loop tracking the sensors are used to detect the position of the sun, which is sent to the system so the microprocessor used in the system can detect the fault and give the necessary control signal to the motors to adjust the fault. This is done regardless of the driving system used to move the tracker. If it's a passive system or another algorithm, set mathematical analysis based on the position of the sun. Load study. It's necessary before the beginning of any electrical design to make careful study of the expected electrical loads of the place, to design the cable, the necessary protection number and rating of the transformers, and to know the requirements for designing a system to generate clean renewable energy when needed. In our case study, we have a house which consists of 3 rooms, 2 bathrooms, corridor, and the kitchen, with a basement in Canada. The first step is to calculate the expected connected load. Then we apply the demand factor to calculate the maximum demand from the loads. As demand factor is equal maximum demand by connected load house. After consider and calculate all electrical sockets, lighting, and heating loads, the total power required for one house include 3 rooms and 2 bathrooms is 39 kilowatt. Normally, loads don't all peak at the same time. As a result, the load of separate peak load will be always be larger than the total system peak load. As the diversity factor is equal maximum demand divided by maximum diverse demand. Assume the diversity factor equal 1.25 as average, so the maximum diversity demand is equal 39 by 1.25 is equal 31 kilowatt. Actual load. Now we have the maximum design load to have the suitable cables with the proper rated current related to the maximum load. The appropriate protection of circuit breakers and panel and transformer that can fit the load. But in our case, we need to give the house an extra renewable energy system tied to the grid. So the design will be done to cover half of the load, which will be around 15 kilowatt. The maximum load is only happening on the rush hours, and most of the time of the day the load will be much lower. So we have to use the total daily load distribution to have a good design, not an over design with only the maximum load.
Now we will speak about how the simulation was created. The study required 2 different models to proceed forward. The first model was implemented by Homer Pro software to study and analyze the sizing and the economics of the model, while the second model was implemented by MATLAB Simulink to analyze the dynamics of the model, as well as to validate the system sizing of Homer Pro software. Here we will talk about the location of our load, which is located inside Canada, British Columbia, with the following postal code, which is inside Vancouver, and our load is only one house, with peak load month in January, and the peak load is 20 kilowatts. And sure, the peak load is inside winter, because we always open the heating systems. The first software we will use in our modeling is Homer Pro software. This is to optimize the system and to design the best option for renewable power generation. Our system contains a photovoltaic array and an inverter connected with the grid, which is already feeding our load. The project life is 25 years, and the capital cost for grid connection assumed to be 0, as the house is already connected to the grid. In this part, we will talk about how the dynamic simulation system was built. The main purpose behind the dynamic simulation is to study and analyze the power output of the PV panels here, under the maximum power point tracking control and the connection with the grid, in addition to the system response when it's connected to the peak house load, which was calculated before in the load study. The system model consists of 2 main parts. The first one is a DC system, which includes the PV power and the buck converter with the maximum power point tracking algorithm control, which uses the incremental conductance method, as shown in the figure here, to control the duty cycle of the buck converter's main MOSFET. In the second part of the system is an AC system, which includes the grid, and a transformer which has one primary winding and two secondary windings to get a two-phase output, which will be then fed to the load. The two systems are connected by one phase inverter, which has a DC input voltage, and the output is one phase AC voltage with 60 Hz frequency to meet the Canadian standards. This inverter is a PWM controlled, as the voltage is pure without harmonics, as we used LC passive filter. The first part of the results we had is from Homer Pro model. The PV array annual energy output is more than 90,000 kWh, with very low excess electricity percent. In our system, no batteries needed, as it's not important to have energy storage while having a grid connection, as if we have excess electricity, we sell it directly to the grid, and then we can buy it again with a reduced price, anytime if needed, as the grid is considered as an infinite power source for our house. In this part, we have some results for the economical side from Homer Pro model. Our solar system, which includes PV panels and an inverter, has total cost of $50,000, but in a long running time it will be a very economical solution, as the expected lifetime of our project is 25 years. In this part we will discuss the final results of the dynamic simulation, which is done by Simulink. Homer Pro PV sizing is 50 panels to feed 50% of the load, which is big house in Canada. So our simulation will use an array of 5 strings, and each string contains 10 PV panels to have total output power, as shown in the next figure, of 16 kilowatts in steady state and after the transient response. The output of the PV panels is DC voltage, then it's connected to an inverter. Here in the slide, we will see the inverter output voltage, which is, as shown in the figure, is a pure sinusoidal wave, and also with frequency equal 60 Hz to meet the Canadian standards. As shown in the first graph, the phase-to-phase voltage is a 340 volts peak, with approximately 240 volts RMS. And in the second graph, the phase-to-neutral voltage for each phase, which has approximately 120 volts RMS. All the waves has 60 Hz frequency and pure of harmonics, with a quick transient response while connecting the load part by part in the system startup. In this slide, we will see each phase current in the load side and the total power consumed by the load. According to the figure, the system can feed the load with very high stability, and the total amount of power consumed by our home load is around 30 kilowatts. In the second graph, we can see the phase current for each of the two phases. During our starting, due to connecting the load, we can observe the transient reaction, but in the steady state, it's a pure sinusoidal wave. In conclusion, after conducting a comprehensive study of the expected loads for a large house in Canada, in Vancouver, a system was designed to generate electricity by solar energy only to feed half of the load of this house. Starting with Homer Pro, which recommended the use of an array of PV panels containing at least 50 panels with a 50 kilowatt inverter connected in combination with a grid to feed the entire load. Then dynamic simulation was done by Simulink with the use of maximum power point tracking control algorithm. Use incremental conductance to produce the maximum power point for the PV array, and the results were excellent and very stable when the maximum load was connected to our design system. Thank you all for your listening, and we are ready for any questions from you. Thank you.